Hello. In lecture number 1, we talked about Newton's second law of motion. So that's given by the force vector as equals to mass times acceleration. Now, this particular force can be also written in two other forms. We have force vector as equals to mass times rate of change of velocity. So this is Newton's law, I can say Newton's second law in a first order form. So, or you can write this equation in terms of the position. So that means force vector is equals to m times the second derivative of the position vector r. So this is in the second order form. Or you can say this is a second order ordinary differential equation. Our primary objective will be to solve equation 1 or equation 2. If we solve equation 1, then we are going to get velocity as a function of time, and if we solve for equation number 2, then we are going to get the position with respect to time t. So this is what the Newton's law entails. Our goal will be to find out the position vector and the velocity vector. So if we have these two information, the position vector and the velocity vector, then we can derive the entire trajectory of a particle. So that is what is going to give us the equation of motion. Fine. So let's try to apply this formula, and this is the problem of the falling raindrop. So let's assume that we have a raindrop. This raindrop has a mass of m, and this is falling through air. As it falls through air, since it has a mass, it's going to be falling under the influence of gravity. So we have mg, and this is the force due to gravity. It's falling downwards. As this raindrop falls through the atmosphere, there is going to be a change in momentum. The question is its velocity going to keep on increasing? Turns out it does not. The velocity of this raindrop reaches a particular value, and once that value is reached, it becomes almost constant throughout its journey. That is happening because as it falls through the air, or as it falls through the atmosphere, the air in the atmosphere, it's going to give a force in the opposite direction. This is a result, or this is a consequence of Newton's third law of motion. So we are going to call this force as the resistive force. This resistive force is proportional to the velocity. That is given by negative k times velocity, where k is a constant of proportionality, and this value of k is dependent on the dimension of the object as well as the fluid or the air through which it is flowing. Now, what we are going to do here, for the sake of simplicity, this f of r, we are going to consider it as the resistive force. We're going to define this f of r as the resistive force per unit mass. That means we have f of r divided by the mass m is equals to negative k times v. So f of r, the resistive force, is equals to negative m times k times the velocity. Now we're going to write down the equation of motion. For that, we have to set up this particular problem. So let's say this raindrop starts from this position, y is equals to 0, and it's going to fall downwards. This is the position of our ground, which is at a height of h. That means our initial position from where the ball starts to fall is at a height of h from the ground. Now, the total force acting on the object will be due to the gravitational force Fg as well as the resistive force acting on it. This will be plus mg. Now this is extremely important how we choose the sign of the gravitational force. Here I am choosing plus. The reason being, our reference position is set at y is equals to 0, where the raindrop is starting. Now from here we are seeing that the raindrop falls down. So that means in the direction of descent, the height is also increasing. Because as the raindrop falls down, its height is also increasing from y is equals to 0 to y equals to h. So for that case, we have to consider f of g is equals to mg. There is another scenario, like if we have considered the ground as the 0 position and that it starts from a particular height, then what happens as the raindrop descends downwards, the height is decreasing. In that case, fg will be equals to negative mg. Fine. So let's proceed with the problem. So f total will be equals to mg minus mkv. Fine. So we have the total force acting on the raindrop. Now, from Newton's second law, F total will be given by mass times rate of change of velocity. And that will be equals to mg minus mkv. Dividing both sides by mass, we get dv over dt. Let's take only the scalar value, so we can get rid of the vector. So dv over dt is equals to g minus kv. Now, the whole idea of considering F of R, the resistive force, as resistive force per unit mass, so that we could get rid of that m in this particular equation, in this first order differential equation. In doing so, now we have a very simple differential equation of the first order, and by using the method of separation of variables, we can find the solution v of t. So let's do that. So we have dv, differential dv, divided by g minus k times velocity equals to dt. Now that we have separated the differentials, we are going to integrate both sides. Now for the first integral, the limits will be from v equals to 0 to v equals to v. And for the second integral, the time is calculated from t equals to 0 to t equals to t. So integration of dv over g minus kv will be negative 1 over k times natural log of g minus kv, with the limits running from 0 to v, which is equals to t, with the limits going from 0 to t. Let's plug in the value of limits. So we have negative 1 over k times natural log of g minus kv minus natural log of g, which is equals to t. Natural log of g minus kv minus natural log of g will be simply g minus kv divided by g. So here what we have done is we have used the property that log of a minus log of b, that simply equals to log of a over b. So this is equals to negative kt. Let's get rid of the logarithm. So we'll get g minus kv divided by g, and that's equals to e raised to the power of negative kt. Or we have 1 minus kv divided by g equals to e raised to the power of negative kt. Solving for the v, velocity, we get v is equals to g over k times 1 minus e raised to the power of negative kt. So we have obtained an expression for velocity, which is a function of time t. So this is a velocity expression. Now from this expression, we can quickly draw a graph of the dependence of velocity with time. So here when time t is 0, we have v of 0 is equals to 0. And when t approaches infinity, we calculate t at a very large amount of time, and then when t approaches infinity, then v of t will approach g of k, and this is also known as the terminal velocity vt. So that means our expression will then be given by v of t equals to v of t times 1 minus e raised to the power of negative t divided by t naught, where 1 over k is t naught. This is the time constant. This is the time constant, and v of t is the terminal velocity with the value g over k. So let's plot this. When we plot it, so we are going to plot the velocity function with respect to time. So at 0 we'll have v equals to 0, and as time approaches infinity, it's going to plateau to a fixed value of vt, which is equals to g over k. And for this graph, the time constant will be 1 over k. When we wrote the equation of motion by using the formula m times dv over dt equals to mg minus mkv, the resistive force, which was F of r, was defined as resistive force per unit mass. If we do not consider the case of that resistive force is defined as resistive force per unit mass, that's it's only simply F of r given by negative k times v, then we will have m dv over dt equals to mg minus kv. Now dividing both sides by m, we have dv over dt equals to g minus k over m multiplied to velocity v. Now we have separated differentials, and that should give us dv divided by g minus k over m times the velocity v, and this is equals to dt. Now that we have the differentials in the separable form, we can integrate both sides. So that should give us integration dv divided by g minus k over m times v, where velocity is going from 0 to v, which is equals to integration dt with time running from 0 to t. So that should give us negative m over k times natural log of g minus k over m times the velocity v, with the limits going from 0 to v equals to time t, the limits going from 0 to t. So let's solve for this. We should get negative m over k times natural log of g minus k over m times v minus log of g, which is equals to t, or simply log of g divided by g minus k over m times v whole divided by g, and this is equals to negative kt over m, or 1 minus k over mg times v equals to e raised to the power of negative kt over m. Solving for v, we have v is equals to mg divided by k times 1 minus e raised to the power negative kt over m, which is equals to v is equals to vt times 1 minus e raised to the power negative t over t naught, where v of t, the terminal velocity, is given by mg over k, and the time constant t naught is given by m over k. Now this particular equation, it's very much similar to what we obtained in the previous problem, except for the fact that K is getting replaced with K over M. Now in the previous problem we had T naught is equals to 1 over K, so that means the unit of K was second inverse, and in this particular case we have T naught is given by M over K, so the unit of K will be kg per second. Let us now note down the result obtained in both the two scenarios. So we have V equals to V of t times 1 minus e raised to the power of negative t over t naught. In this case, V of t is given by g over k, and t naught is defined as 1 over k. This is the case. This was the form that we are going to use when we have the force, the resistive force given as a resistive force per unit mass. And in the second case, we have V is equals to V of t times 1 minus e raised to the power of negative t over t naught, where V of t will be given by mg divided by k times t naught is equals to m over k. These two equations that we derived just now finds their application in a very important experimental problem referred to as the falling ball viscometric problem. So let's try it out. Let us consider a cylindrical column that contains some viscous liquid. So we are going to make a spherical ball fall through this viscous liquid. The spherical ball has a mass of m and radius r. Now when this ball falls through this viscous liquid, it's going to attain a terminal velocity. That is because of the viscous force that's acting on it. So viscous force will be in the opposite direction. So we have a downward force, which is the force due to gravity, that is mg, acting downwards. We have the viscous drag force, let's call it F of R, the resistive force, which is acting upwards. And of course, there's always going to be the buoyancy force, F of P, which is also going to be acting upwards. So let's note them down. So we have downward force, which is given by Fg equals to mg. Then we have two upward forces. So upward forces, one will be the buoyancy or the buoyant force, that's denoted by F of B, and then we have the viscous drag, the viscous drag force given by F of R. Now we need to write down the force equation. So the total force acting on this spherical ball will be equals to mg minus the buoyant force minus the viscous drag force. So let's label this as equation number 1. Now we need to find out Fb and Fr first. The buoyant force F of B is given by the volume of the spherical ball multiplied by the density of the viscous liquid or the viscous fluid times the acceleration due to gravity. So this will be equals to, so the volume of the spherical ball will be given by 4 by 3 pi r cubed, where r is the radius of the spherical ball, times the density of the fluid. So let's assume that the density of the fluid is given by rho times the gravity. So this is our Fb, the buoyant force, and the viscous drag force is given by Stokes' law. So the Stokes' law states that we have 6 pi eta times rv. So here this V is the instantaneous velocity. Instantaneous velocity. This is the velocity of the ball as it falls through the viscous liquid. Eta, this is the viscosity of the liquid. This is the viscosity. Actually, in this problem, this is what we need to find out, the viscosity of the given liquid. And this equation f of r equals to 6 pi eta rv, this comes from Stokes' law. Now, couple of notes that I'd like to mention before proceeding forward. This equation fr equals to 6 pi eta rv, this equation is only valid for spherical objects like the one we have considered in this particular problem. And also this equation is very ideal, meaning that this 6 pi, this particular term will have a correct term. However, for this particular problem, this is not of much importance right now because this can be treated as a constant. We will be only focusing on eta, r and v. So let's plug in this value of fr and fb into equation 1. So we have F total force is given by mg minus the buoyant force. So the buoyant force will be 4 by 3 times pi r cube times rho times g minus 6 pi eta times r times v. Here m, which is the mass of the spherical ball, and the mass will be given by, since it's spherical in nature, we have the volume 4 by 3 pi r cubed multiplied by the density of the solid ball. So let's write it down that this is the density of the ball, such that our equation now becomes F total as equals to mg. So we have 4 over 3 times pi r cubed times sigma times g minus 4 by 3 pi r cubed times rho times g minus 6 pi eta r v. And this total force is m times dv over dt. So we first try to find out the expression for the terminal velocity. In order to find out the terminal velocity, we are going to set the derivative dv over dt as equals to 0, and that is the definition. That's the velocity once the terminal velocity is obtained, the velocity of that object becomes constant. So we have dv over dt equals to 0. So when we set this equation equals to 0 and we write the equation in terms of the terminal velocity, so we will get 0 equals to 4 over 3 pi r cube times g. So we are taking this as the common factor from the first and the second term, so that leaves us with sigma minus rho minus 6 pi eta r. So this will become now the terminal velocity vt. So let's call this as the terminal velocity. So solving for vt, so we get v 6 pi eta r times vt is equals to 4/3 of pi r cube g times sigma minus rho, dividing both sides by 6 pi eta r. So we have the terminal velocity vt equals to 4 pi r cube times g divided by, so we have 3 times 6, so that will be 18. 18 pi eta times r into sigma minus rho. So here we can see that the pi and pi gets cancelled. 1 r from the denominator and 1 r from the numerator gets cancelled. 2 times 2 is 4 and 2 times 9 is 18. So our expression of vt becomes the terminal velocity vt is equals to 2 over 9 times r squared g over eta multiplied to sigma minus rho. So here we have the expression for the terminal velocity. Now, in an experiment of the falling ball viscometer problem, what we are going to do is, let's redraw the diagram. So we are going to set two cameras here. This is, let's say, camera 1, and this is camera number 2. With the help of camera 1, we are going to make a note of the position of this spherical ball and let it fall through this viscous liquid, and after it traverses a distance of, let's say, L units, it's going to reach a particular distance. Now we are also going to make a note of the position of the sphere at this particular point. So using the time elapsed, we can say that our terminal velocity v of t will be equals to L over t. So let's equate both the two equations. So we have distance traveled L divided by the time taken is equals to 2 over 9 times r squared g whole divided by eta times sigma minus rho. Solving for eta, so we have eta is equals to 2 over 9 times r squared g over L times sigma minus rho multiplied to t. Now in this equation, 2 over 9 is a constant, the r radius of the spherical ball is known, g is also known, the distance L, this can be fixed, and the sigma and rho values can also be known. That means all we have to know is if we can measure the value of this particular time t accurately, then we can measure the viscosity of the liquid, and that is given by eta. So this is the problem of the falling body viscometer problem. So using this problem, what we have done, we have measured the viscosity of a liquid by first setting up the equation of motions, which is a first order differential equation. Couple of notes that I need to make before moving on. Here I'm in this force, the viscous drag force that was mentioned here in this particular problem, which is f of r is equals to 6 pi eta r times v. So this is going to be valid, or you can say this is a very good approximation when our velocity v is extremely small. So this is a very good approximation, but there are certain cases when v is very large, and that's when we are entering the region of turbulence flow. So that means if we are working with a very high velocity scenario, then we are in the pressure drag domain. So we'll be using the formula f of p equals to half c rho times a times v squared. So here a is the effective cross section of the object, rho will be density of the fluid or the liquid through which the object is flowing, and c is the shape factor and it's related to the geometrical shape of the object that is being used, and v is the velocity. Anyways, these terms are not that important for this particular idea here. What I'm trying to mention here is that this force, this pressure drag force, is essentially proportional to the square of the velocity. So this is the key. So that means whenever we're working with very high velocity problems, we will be using this formula f of p is equals to negative kv squared. Let's work on few numericals to understand what we have just talked about. Problem number 1. In this problem, we are given that a motor vehicle is being driven with some constant force F, and it encounters a resistance that is proportional to the square of the velocity. So let's draw a quick diagram. So let's say that we have a motor car, and that's traveling under the influence of some force F, and this force is constant. So initially it's going to gain some velocity, and after a certain period of time its velocity is going to attain a maximum velocity of u, and after that it's going to keep on moving with a constant speed. Now as it moves, it's also going to get encountered by air resistance, which will be in the opposite direction. Let's call it f of r. Now it is given that this air resistance f of r is given as it's proportional to the square of the velocity. So that means it's of the form negative kv squared. Now, unlike the problem that we encountered earlier for the case of a raindrop or a ball falling through a viscometer, this motor car has comparatively a higher velocity. So that means we are in the pressure drag regime. So that's why it has a v square dependence. So let's write down the equation of motion. So we have m times dv over dt, and that is equals to the constant force F which drives the car, plus we have f of r. Right? This is equation number 1 and this is equation number 2. Now we have to show that the car's acceleration varies as u squared minus v squared at a speed of v if u is its top speed. So that means this car is moving under the influence of this constant force F. So what happens? As it moves forward, the air resistance is going to slow this car down. It will try. There will be a point when exactly F will be balancing FR. They're exactly going to balance each other. So in that case, when it balances each other, we said that the velocity with respect to time is equals to 0. So that means we have 0 is equals to F. So FR is minus K U square. So this is the case when the velocity attained is maximum. So we have negative KU squared. So that means we get F is equals to KU squared. Let this be equation number 2. Now let's substitute 2 and 1. This is equation number 3. Let's substitute 1 and 3 into our equation number 2. So that gives us m dv over dt. So that will be equals to, so we have F. So F is KU squared minus FR, which is the drag force. So that is KV squared. And if we take K as the common factor, we have U squared minus V squared. And that is the solution that proves it, that the car's acceleration, which is dv over dt, so that is proportional to U squared minus V squared. Let's move on to the next problem. Problem number 2. So here we are given that a skydiver acquires a terminal velocity of 24 kilometers per hour upon falling from rest. Find out how long it takes to reach the terminal velocity, assuming that the air resistance is proportional to the instantaneous velocity. So here we are given that the air resistance is proportional to the instantaneous velocity. That means that the drag force F of r is given by negative kV, such that the velocity expression v of t is given by v of t times 1 minus e raised to the power negative t over t naught. This is an expression for the velocity. Now in this question, it's given that v of t is equals to 24 kilometers per hour. So we need to convert it to the standard meters per second. So that will be 24 times the kilometer is 1000 meters divided by r. So in 1 hour we have 60 minutes times 60 seconds. So this is now converted to seconds. Upon solving this, we get 20 over 3 meters per second. Fine. So we have the terminal velocity, which is 20 over 3 meters per second. Now we have been asked here, like, how long does it take to reach this particular velocity, 20 over 3? Then in that case, we know that it takes 5 t naught to reach the terminal velocity. That means we need to find out the value of t naught in order to find out the total time it takes to reach the terminal velocity. So from this expression of the velocity, here we have the terminal velocity vt is given by g over k. So if we solve for k, so that will be equals to g over vt. So g, so to keep our calculation simple. So let's take it as 10 meters per second divided by, so we have Vt. So the Vt is 20/3 meters per second, which will be equals to 3/2. This is meters per second square, so we have 3/2 second inverse. So this is the value of K. So now that we have K, we are going to determine the value of T0. So our T0 is given by the reciprocal of this constant of proportionality, 1/k. So that's going to be equals to 2/3 seconds. So we have T0, so that means 5. T0 will be equals to 5 times 2/3. So that's equals to 10/3, which is approximately 3.33 seconds. So that means it takes approximately 3.33 seconds for the skydiver to acquire a terminal velocity of 24 kilometers per hour once it falls from rest. Okay, so this is the end of today's lecture. See you in the next lecture. Thank you.